Welcome to the debate. Today, we are stepping into perhaps the most hallowed territory in all of physics. We're talking about the equivalence of mass and energy. We all know the equation. It's likely the only formula your grandmother knows, and certainly the one that defines the modern era. E equals mc squared. It suggests a universal invariant exchange rate between matter and energy, governed solely by the speed of light. It's elegant, it's absolute, and it's the bedrock of relativity. But what if I told you that this formula is actually a special case? What if Einstein's famous identity is merely the asymptotic limit for a free, unbounded vacuum? And then in the real world of boundaries, cavities, and nanostructures, the energy ledger is actually quite different.
And that is where I have to step in immediately and, well, urge caution. We're diving into the structured vacuum theory today. And while the idea is intellectually stimulating, and I'll admit, mathematically seductive, suggesting that we need to modify Einstein's rest energy formula is an extraordinary claim. It requires extraordinary evidence. I'm here to argue that while the physics of boundaries, specifically the Casimir effect, is real, rewriting the fundamental identity of relativity is unnecessary, and as we'll discuss, potentially fraught with contradictions regarding how we define motion, frames of reference, and the conservation of energy itself.
I accept the challenge. To be clear, the central question we're debating is this: is the vacuum neutral, or is the vacuum a spectrum? That is written by geometry. My position is that because boundaries modify the vacuum spectrum, which is the foundation of Casimir physics, effective energy accounting must include a topological scaling factor. We call this factor chi-t.
And my position is that standard quantum electrodynamics, or QED, handles these boundary effects perfectly well without inventing new terms for rest mass. I believe that introducing a topology factor into the rest-energy relation risks violating Lorentz invariance, the basic rule that physics should look the same to all observers, and leads to definitions of velocity that frankly just don't hold up to scrutiny when you look at the vector calculus.
All right, let's dive into the position statements. I want to start by laying out the core thesis. We are not saying Einstein was wrong. That's a straw man. We are saying he was describing a specific limit, the limit where boundaries vanish. My argument rests on a unified principle. Constraint writes the choir.
Constraint writes the choir? That's a poetic way to start a physics debate, but I'm not sure how it calculates a force.
It is an analogy, but a precise one. Think about the atmosphere. At sea level, water boils at 100 degrees Celsius. On Mount Everest, where the pressure is lower, it boils at 70 degrees. The water molecule hasn't changed. The intermolecular forces haven't changed. But the constraint environment, the pressure, has changed the energy threshold for the phase transition. The bar has moved.
Sure, that's standard thermodynamics. Phase transitions depend on ambient pressure. No physicist disputes that.
Exactly. And my argument is that the vacuum operates on the exact same structural principle. The vacuum is not empty space. It is a spectrum of electromagnetic modes. In free space, that spectrum is continuous. It's an infinite ocean of potential frequencies. But when you introduce boundaries, like the conductive plates in the Casimir experiment, you truncate that spectrum. You exclude certain wavelengths that don't fit between the walls. You change the pressure of the vacuum. If you change the mode density, you change the energy density. Therefore, the effective energy expression for a system in a bounded environment is not just mc squared. It's E is F equals mc squared qt. That qt represents the ratio of the bounded spectral density to the free spectral density. It's not new physics, it's just honest bookkeeping of the Casimir effect.
That is a compelling narrative, but we need to look at the machinery under the hood. I have read the source papers on this structured vacuum theory. The initial formulation relies heavily on this concept of a transport velocity, denoted as Vt. The theory argues that inside these cavities, energy doesn't flow at c, it flows at an average speed Vt, and therefore your factor chi-t is just cVt.
That was the intuitive bridge used in the early heuristic derivations, yes. It helps to visualize the slowing of the group velocity.
But it's a bridge that collapses under weight.
In classical electromagnetism, we define local energy velocity using the Poynting vector, S, which represents energy flux divided by the energy density, U. The problem, and this is cited as problem A in the literature, is that the ratio SU is frame-dependent. If I'm standing still next to your cavity, I see one energy density. If I start walking, the energy density and the flux change in different ways because of how electromagnetic fields transform. A velocity defined this way isn't invariant. If your rest mass depends on a velocity that changes depending on who's looking at it, you have broken relativity. You're implying that effective mass is frame-dependent, which is physically impossible.
I see why you're zeroing in on that. And I'm glad you brought up the velocity definition immediately, because this is the most common misunderstanding. You're attacking the heuristic, not the physics. The use of VT, this transport velocity, was a mnemonic. It was a way to visualize why the energy changes, sort of like how we teach electron flow as water in a pipe. But the theory has been hardened, if you will. The formal definition of chi-t does not rely on Poynting vectors or transport speeds.
Then what does it rely on? If you abandon the velocity concept, what is the physical meaning? You can't just have a dimensionless number appear out of nowhere.
The physical meaning is the density of states. This is pure spectral geometry. We define chi-t strictly as the ratio of the spectral integral, the sum of all allowed modes in the cavity, to the spectral integral of free space. It's a counting exercise. In free space, you have the full choir of mode singing. Inside a cavity, some singers are silenced by the boundaries. The ratio of the choirs is chi-t. This definition is derived directly from how we calculate Casimir forces using Green's functions. It doesn't care about your frame of reference in the way a simple velocity vector does. It cares about the geometry.
I want to push on that counting the choir idea. Even if I grant you the spectral definition, you run into what I call the standing wave objection, or problem B. In a perfect cavity, you have standing waves. By definition, a standing wave has zero net energy flux. The time-averaged Poynting vector is zero because the wave is bouncing back and forth perfectly. If you were using your old definition, Vt would be zero, and your factor Ct, which you said was CVT, would go to infinity. Infinite energy. That's a singularity.
But again, that singularity only exists if you're wedded to the flux definition. The spectral definition solves this instantly. Does a standing wave have zero energy? Of course not. The energy is stored in the field configuration, its potential. Nodes in a standing wave do not eliminate the spectral density. They just mean the energy isn't translating through space. The spectral sum includes those standing wave modes. So there's no divergence. Chi-t is simply a measure of how much energy is stored in that standing wave configuration relative to free space. It describes the tension of the field, not just the flow. Think of it like a compressed spring. It's not moving, but the energy density is absolutely there.
Okay, let's step back from the math of the waves for a second and talk about the fundamental principles of relativity. Einstein's relativity relies on Lorentz invariance, the idea that the laws of physics don't change just because you're moving. Bounded systems, by their very nature, seem to break this. If you have a box, that box has a rest frame. If your theory relies on the geometry of the box to define the mass of the particle inside it, aren't you explicitly violating Lorentz invariance? You're making mass dependent on the box's frame.
That is an incredibly subtle point. I would frame it differently. You're treating the apparatus rest frame as a bug, but in this context, it's actually a feature. Let me ask you, does a thermometer violate relativity?
A thermometer? No, of course not. It measures the average kinetic energy of particles.
But temperature is frame dependent. If you fly past a cloud of gas at near light speed, the temperature you measure looks different because of Doppler broadening. Yet, we understand that the gas has a rest frame, where the temperature is well defined. Bounded electromagnetic systems are the same. The cavity defines a rest frame. The Casimir effect itself is frame conditioned. You calculate the force in the rest frame of the plates. The theory acknowledges that boundaries break the continuous symmetry of free space. Lorentz invariance applies strictly to the asymptotic vacuum, the free space, but inside the box, the physics is conditioned by the box. We aren't breaking relativity. We are acknowledging that the box exists.
So you're saying E equals mc squared is the law of the open ocean, but once you put water in a cup, the rules change?
I'm saying E equals mc squared is the law of the open ocean, and EF
equals mc squared qt is the law of the cup. And crucially, when the cup gets infinitely large, qt becomes 1, and you get Einstein back. It's mathematically consistent. It recovers the standard limit. It's not a violation, it's generalization.
I am not entirely convinced by that line of reasoning because it simplifies the geometry too much. You talk about qt like it is a simple scaling factor. But anyone who works with Casimir physics knows that the forces don't scale by a simple constant across different shapes. The force between two spheres is different than the force between two plates. It's complex, it's nonlinear. Suggesting there is a single number, qt, that you just multiply mass by, it feels too naive. It feels like you're looking for a magic number.
I agree with you completely. If Ψ were just a constant scalar, the theory would be dead on arrival. But that is a strength of the theory, not a weakness. Ψ is not a universal constant. It is a functional.
A functional? Explain that for our listeners.
A functional is a function of a function. Ψ is determined by the specific geometry, the material properties, and the topology of the system. For parallel plates, it has one value derived from the plate separation. For a sphere, it's derived from the radius. For a toroidal cavity, it involves the major and minor radii. We don't just pick a number, we calculate it using the scattering formalism. We use reflection operators and logarithmic determinants, the standard heavy artillery of modern QED, to compute exactly how the spectrum is distorted.
So you have to calculate it from scratch every time?
Yes. We're not guessing chi, we're computing it. For example, in certain specific toroidal geometries where the effective circulation is high, you might calculate a chi of 1.111. That predicts a precise 11.1% increase in effective energy density. It's testable, it's not just a vague concept.
Testable is the key word here, and this brings me to my biggest issue: scope, discipline. If this were true, if rest mass were actually modified by geometry, we should have seen it. We have particle accelerators, the Large Hadron Collider, smashing particles together with incredible precision. They confirm E equals mc squared to decimal places that make my head spin. If there was a topology factor, wouldn't the LHC have noticed that their protons were 10% heavier?
This is the crucial distinction. Where does the LHC operate?
In a vacuum cube. In a high vacuum, an ultra-high vacuum beam pipe. The pipe is centimeters wide.
The protons are sub-femtometer in scale.
Effectively, the protons are flying through free space. The distance to the walls is huge compared to the wavelengths of the particles. In that environment, the boundaries are negligible. The spectrum is effectively the free spectrum. So chi-t is approximately 1.000000 to a distinct number of zeros. Our theory predicts that the LHC would confirm standard relativity.
So you're saying the effect hides in the noise?
I am saying it only appears where the structure is tight. The theory applies to structured environments, nanoscale cavities, metamaterials, extreme plasma confinement, perhaps the crust of magnetars. We are talking about environments where the vacuum spectrum is violently distorted. You cannot use a free space experiment to disprove a bound space theory. It is like trying to measure water pressure at the surface and claiming deep-sea crush depth is a myth.
I see. So you are creating a scope discipline. You're walling off the theory to places where we haven't looked yet. That is convenient, but logically sound if the math holds up.
I'm applying the same logic as general relativity. Newtonian gravity works great at low speeds. You need GR for high speeds. EF equals mc squared works great in free space. You need EF equals mc squared chi-t for bound space.
Let's assume for a minute that this is valid. How do we prove it? You mentioned that chi-t is a functional of geometry. That implies that if I build a cavity of a certain shape, I should see a deviation in the Casimir pressure that matches your topology factor exactly.
Precisely. And this is where the Steelman argument comes in. We know that Casimir forces exist. We know they depend on geometry. Usually, we treat them as a force added to the system, like a distinct external pressure. I'm saying we should treat them as a modification of the energy density of the system itself. The experiment would be to construct a high-Q toroidal cavity, something with recursive geometry, and measure the Casimir pressure. If the pressure deviates from the standard proximity force approximation by exactly the ratio predicted by the spectral density change, then chi-t is real.
That brings me to the fifth force objection. If you modify the effective mass of a system based on its container,
Do you violate the equivalence principle? Does a heavier vacuum cavity fall faster in a gravitational field? Because if it does, you have a violation of the weak equivalence principle, and that is a fast track to getting your theory ruled out by Udovis experiments, which measure how things fall to incredible precision.
That's a very dangerous trap to fall into. It relies on thinking of chai tea as a scalar field that permeates the universe, like a magical ether. It isn't. It's a local modification of energy content. Let's look at the binding energy of a nucleus. A nucleus weighs less than the sum of its protons and neutrons, right?
Sure, that's the mass defect. That is where nuclear energy comes from.
Does that mass defect violate the equivalence principle?
No, the nucleus falls exactly as its total energy mass dictates. Similarly, a cavity with modified vacuum energy has a different total energy content. It will respond to gravity according to its total energy. We aren't adding a fifth force, we're correcting the mass label on the box. Gravity pulls on energy. If the geometry changes the energy, gravity pulls on that new amount. It's fully consistent with general relativity.
I'm sorry, but I just don't buy that it's fully consistent without a full Lagrangian formulation. You can't just modify the energy density U without modifying the stress tensor and the momentum density. If you change one, you have to change them all to keep the conservation laws intact. If X is just a multiplier on energy, you break the conservation of the stress energy tensor. You'd have energy appearing out of nowhere or momentum not being conserved. You are absolutely right to call that out. If this were just a scalar multiplier slapped onto the energy term, the math would break. That's why the hardened theory isn't just a multiplier on U. The spectral modification affects the entire stress energy tensor. When you change the mode density, you change the pressure components and the shear components too. Psi t is the summary statistic of that change, but the underlying math, the scattering matrices, handles the full tensor. We are not just painting a new number on the energy, we're solving Maxwell's equations with boundary conditions. By definition, Maxwell's equations respect conservation laws.
I think we're reaching the crux of the disagreement. I'm willing to admit that the hardened spectral definition avoids the mathematical fatalities of the velocity-based definition. You've successfully dodged the problem A of frame dependence by anchoring yourself to the apparatus frame, and I have to admit, Casimir physics proves that boundaries matter. You can't deny that.
Exactly. The vacuum pushes back.
However, I remain cautious. You're asking us to view Einstein's identity as a special case. That is a massive conceptual shift. The extraordinary claim of modifying the energy-mass relation requires extraordinary evidence. I want to see chi-dar measured. I want to see a control geometry where the effective energy density is demonstrably different from standard QED predictions in a way that can only be explained by your topological factor. Until then, it is a beautiful mathematical structure, but is it physics? Or is it just geometry pretending to be physics?
And that is the fair demand. Physics is an experimental science. But let me leave you with this perspective. We used to think space was empty. Then we found it was a vacuum. Then we found the vacuum had fluctuations. Then we found those fluctuations could push plates together. The history of physics is the history of realizing that the background is not inert.
That's true. We have been filling the void with fields for 100 years.
My final point is simply this. Constraint writes the choir. The choir writes the energy ledger. Einstein is the limit where the choir sings in an open field. But most of the interesting universe, and certainly our future engineering, happens inside the cathedral. The vacuum is not neutral to geometry. Chi, Q, is simply the factor that admits this. We must compute it and we must measure it.
Well, it certainly gives us a lot to think about. The next time we look at a vacuum chamber, it's not just emptiness. It's a geometry waiting to be written.
Precisely.
We want to thank you for listening to this deep dive into spectral geometry and the nature of mass itself. It is complex, it is controversial, but that is why we love it.
Thank you for engaging with the complexity. There is always more to explore in the material.
Until next time.
I want you to picture the most famous equation in the world. You don't even need to be a physicist to see it. It's on T-shirts, coffee mugs, cartoons.
Oh, everywhere.
The side of buses.
Yeah.
It is like the 3-chord pop song of the scientific world.
MC2 one.
Exactly. Energy equals mass times the speed of light squared. It is so elegant, it's symmetrical, it's, the cornerstone of modern physics.
It absolutely is.
It tells us that mass and energy are basically the same thing. They're just wearing different hats. It governs everything from nuclear power to the sun itself.
It's the equation that really defined the entire 20th century.
Right. But, and I need everyone to stay with me here for a second because this might sound a little blasphemous. What if it's not the whole story?
And that is the big question we're asking today.
I was reading through this stack of research you sent over, this proposal for something they're calling a structured vacuum, and I literally had to put my coffee down.
I get that.
Because the core argument here isn't that Einstein was wrong. We are not doing the whole Einstein was a fraud thing you see on the internet.
Absolutely not. No, Einstein was brilliant, and special relativity is, it's one of the most rigorously tested theories in history. We are not throwing that out.
But the argument is that Nolio equals MC232 is technically a special case.
A special case, yes.
It's the equation for a specific kind of idealized scenario that almost never actually exists in the real world of technology. It's the equation for free space.
Precisely. And that one distinction between free space and what this research calls bounded space, that is everything.
So if I'm getting the mission of this deep dive right, we're going to explore this idea that the vacuum, empty space, it isn't just a background.
It's an empty stage.
Right. It's not just an empty stage where matter dances. The stage itself has a shape, and that shape changes the value of the matter itself.
You've just hit the nail on the head. That is the central thesis we're going to unpack. The geometry of the space you are in dictates the energy interactions within that space.
So if you change the shape of the room,
you change the energy of the objects inside it.
Which sounds like magic. It sounds like you're saying, I put a box around a battery and the battery's energy changes.
It does sound like magic, I'll grant you that. But by the end of this hour, I hope to convince you and everyone listening that it's actually just rigorous, albeit overlooked, thermodynamics.
Okay, let's start at the very bottom then. Definitions. When we say the vacuum, I think most listeners, myself included, immediately imagine outer space. Or, I don't know, the inside of a thermos, just nothing.
Yeah.
Abscess.
And that is the classical intuition for sure. If you take a box and you suck all the air out, take all the atoms out, shield it from radiation, you're left with nothing.
Yeah.
But in quantum mechanics, nothing is a very, very busy place.
Okay, this is the 0-point field, right?
Correct. The vacuum is not empty. It is seething with potential energy. We usually call them electromagnetic fluctuations, virtual particles popping in and out of existence all the time. But for the sake of this theory, I want you to visualize it a little differently. Don't think of particles for a second. Think of waves.
Waves, got it.
Think of the vacuum as a spectrum, a collection of every possible frequency of electromagnetic wave, all vibrating at once. The source material uses a great analogy. It's like a choir.
A choir.
Yes, an invisible universal choir. And it's singing every single note on the piano, plus notes way, way lower than the piano can go, and notes way, way higher, all at once. That's the constant background hum of the universe.
So in free space, deep, dark, empty space where there's nothing for light years, this choir is singing.
Everything. Absolutely everything. In free space, there are no walls. There are no boundaries. So the choir can sing any wavelength it wants.
Any note.
Any note. It can sing it with a wavelength of 1 billion miles or a note with a wavelength of a nanometer. There's zero restriction.
Okay, so free space is like an open field. Total freedom for the choir.
Exactly. And that is the idealized world where Einstein's equation lives. Del A equal E, or a 2, assumes that the background, that the stage, is this infinite, unrestricted, open field.
But, and this is where this research gets really spicy, we don't live in an infinite open field. We live in a world of stuff.
We do. We build engines, we build computer chips, we build batteries. All of these are bounded spaces. They have walls, they have geometry.
And this is where that choir analogy really made things click for me when I was going through the notes. If I take that universal choir and I shove them into a small broom closet, they can't sing the low notes anymore.
Exactly. This is the core concept right here. It's called spectral geometry.
Yeah.
If you have a wave that is, say, 10 meters long, a nice deep bass note, but your room is only 1 meter wide, that wave physically cannot fit in the room. It is excluded from the performance.
So it's not just that the bass note is quieter, it's gone. It's not allowed to exist in that space.
It is suppressed. The density of states, which is just a fancy physicist way of saying the menu of available options, it shrinks. The geometry of the container literally limits the spectrum of the vacuum.
Geometry dictates the spectrum.
And here's the kicker. Here's the whole point. Energy is linked to that spectrum. So if you remove the base notes, you have fundamentally changed the total energy density of that space. You have altered the vacuum itself.
Okay, so let's bring this back to the equation then. We have Wei equals mc2. But this research paper proposes a modification. I'm looking at it here in the notes, and it looks like someone hacked Einstein.
It's a modification, yes.
Yeah.
It's a generalization.
The formula they give is E, I feel MC2, chi S. That last that's a Greek chi, right? Subscript T.
Yes, that's chi T. It stands for the topology factor.
Okay, break this down for me. What does this chi T actually represent? What is it doing in there?
It represents the environment. It is a scaling factor, a multiplier.
So it's like a volume knob for reality.
That's a great way to put it. Think of it this way. In free space, on that infinite salt flat where Einstein did all his thought experiments, the topology factor, TT, is exactly 1.
Okay, and if I multiply anything by 1, it just stays the same. So W equals MC2 times 1 is just W equals MC2.
Exactly. The new theory doesn't break the old theory, it contains it. It just says, Einstein, you were absolutely right, assuming your TD is 1 Lars.
But the moment I step off that salt flat and walk into a building, or more specifically inside a tiny nano cavity and a microchip, TT isn't 1 anymore.
Right. In a bounded space, a structured vacuum, the value of TT shifts. It might be 0.9, it might be 1.1. It depends entirely, and I mean entirely, on the shape of the space.
So effectively, the energy value of mass changes based on where that mass is sitting.
Yes. The effective energy changes because its interaction with the vacuum, with that choir, has been altered by the walls.
Now, I have to pause here, because when I first saw this in the notes, I saw a slightly different version of the formula. In one of the earlier drafts, or maybe it was in an appendix, it was written as AD equals MC3 VT.
Ugh. Yes. The infamous velocity formulation.
Yeah, I looked at that and my brain threw an error code. MC3 $3. Are we cubing the speed of light now? And dividing by some other velocity, $5 is. That feels like it breaks every rule in the book.
It does.
Specifically relativity. I mean, if you start talking about variable speeds of light, usually you get politely shown the door at the physics conference.
And rightly so. That is a very dangerous and misleading path. This is actually a fascinating part of the intellectual history of this idea. The author initially used $5, which stood for volumetric transport, as a heuristic.
A heuristic? You mean like a metaphor, a teaching tool?
A mental shortcut, exactly. The idea was to help people visualize that energy doesn't travel in a straight line inside a complex shape. It has to bounce around. Imagine running through a maze. Your straight line speed from start to finish is low because you're constantly hitting walls and turning. Your transport speed is slower.
Okay, that makes sense intuitively. I get that.
It makes sense intuitively, but mathematically, it is an absolute trap. If you treat that $V as a real physical velocity, you run straight into the frame dependence problem.
Okay, explain that. What's the frame dependence problem?
Okay, so a core principle of relativity is that speed depends on who is watching, the observer.
Right.
If I'm on a train and I throw a ball, the ball is moving, say, 10 miles per hour to me. But to you standing on the ground as the train speeds past, the ball is moving at 100 miles per hour. Speed is relative.
Got it.
But the laws of physics, like how much energy is in a battery, shouldn't depend on who is watching. They need to be fundamental. So if your core formula relies on a speed that changes depending on the observer, well, you haven't written a law of physics, you've written a subjective observation.
So the critics would immediately say, hey, your $V changes if I just walk past the experiment at a different speed, so your entire theory is bunk.
Exactly. That is the Steelman objection, the strongest argument against it. And to their credit, the source material explicitly acknowledges this. They moved away from the velocity language for precisely this reason. It was a useful starting point, but it was dead end.
So what's the fix? How do you keep the core idea without the bad math?
We go back to the choir. We go back to spectral density.
Okay.
You stop trying to measure the speed of the waves, which is frame dependent, and you start measuring the density of the wave.
I don't.
The count, the intensity, the loudness of the vacuum in that specific space. That is a geometric fact. It doesn't matter how fast you walk past a cathedral. The acoustics inside the cathedral are determined by the walls, the ceiling, the shape.
I see.
The spectral density is frame independent in the rest frame of the cavity. It's a property of the system itself.
Okay, that is a absolutely crucial distinction. So we're not, I repeat, not saying light slows down. We're saying the availability light waves, the spectrum, the choir songbook changes.
Yeah. Perfectly put. We've moved from the kiddie table of velocity metaphors to the adult table of spectral density calculations. And that GT factor, GTT, is just a ratio of that density compared to free space.
Okay, I'm with you on the theory. It's elegant, geometry changes the spectrum changes the energy. But right now, this is all just scribbles on a whiteboard. I am a skeptic at heart.
As you should be.
I need to know, is this real? Is there any experimental evidence for any of this? Or is this just some very clever math fiction?
It's a completely fair question. In theoretical physics, it is very easy to invent a beautiful universe that looks pretty on paper but has no connection to reality. But in this case, we have an anchor, a proof of concept that has been experimentally verified for decades.
The Casimir effect.
The Casimir effect.
Now, I've heard this term thrown around in, science fiction. Casimir energy, zero-point modules, all that. But walk us through the actual real-world science. What is it?
So we have to go back to 1948. A Dutch physicist, Hendrik Casimir. He's working at Philips Research Labs. And he predicts something that sounds absolutely insane. He says, take two metal plates, perfectly uncharged, no magnetism, no static electricity, just inert pieces of metal. Place them in a perfect vacuum, completely isolated.
Two dead pieces of metal floating in nothing. Got it.
Now, bring them very, very close together, a few nanometers apart, closer than the width of a virus.
And what happens?
They push together.
Attract.
They attract. A mysterious, invisible force grabs them and pulls them toward each other.
Wait, hold on. If they aren't magnetic and they aren't electrically charged and gravity is way too weak to matter at that scale, what is possibly pushing them?
The vacuum. Or rather, the difference in the vacuum on either side of the plates.
Oh, back to the choir analogy.
Exactly. Let's think about our choir again.
Yeah.
Outside the plates, in the race of the universe, the choir is singing every possible note. The radiation pressure of all those waves is pushing on the plates from the outside.
It's pushing inwards.
Pushing inwards from all directions. Now look at the tiny space between the plates. The gap is minuscule. It's so small that the long wavelengths, our deep bass notes, literally cannot fit. They are excluded from the performance in that gap.
So the part of the choir stuck between the plates is missing half its vocalists.
Right. The energy density inside the gap is lower than the energy density outside the gap.
So you have high pressure outside, low pressure inside.
And nature abhors a vacuum, or in this case, a pressure differential. The higher pressure from the outside smashes the plates together.
That's wild. It's literally the force of nothing pushing on something.
It is the most direct, undeniable proof we have that the quantum vacuum is not empty. It has structure. It has energy. And this is the critical part for our deep dive today. The geometry determines the force. Well, if you move the plates closer together, the force gets stronger because you're excluding even more wavelengths. If you move them apart, it gets weaker. And if you change the shape, if you use a sphere and a plate instead of two flat plates, the mathematical formula for the force, the scaling law, changes completely.
So Hendrik Casimir basically proved that geometry dictates energy all the way back in 1948.
He did. He proved experimentally that boundaries change the energy state of the vacuum. The theory we are discussing today, this structured vacuum idea, is really just taking Casimir's verified discovery and asking the next logical question. Okay, if this force is real, why aren't we applying this logic to EMC22?
It's that Steelman argument again. It's a chain of logic. Premise 1, boundaries change vacuum energy. Casimir proves this.
Check.
Premise 2, mass is a form of energy. Einstein proves this.
Okay.
Conclusion, boundaries must affect the energy accounting of mass.
You cannot logically separate the content from the container. The container is part of the system.
I want to pivot here because talking about nanometers and metal plates is fascinating, but it's a little abstract. It's hard to feel in your gut. The part of the source material that really made the light bulb go off for me was the analogy about boiling water.
Ah, yes. The bar gradient argument. This is where we leave the quantum world for a moment and go to simple high school thermodynamics. But the underlying logic is identical.
So picture a pot of water, you put it on a stove, you turn on the heat.
Simple enough. We've all done it.
If I'm in my kitchen in, say, New York City, which is basically at sea level, that water boils at 100 degrees Celsius, 212 Fahrenheit.
Correct. The atmospheric pressure is about 1 bar.
Now, I pack up my stoves and my pot, and I hike up Mount Everest. I'm at 29,000 feet. The air is incredibly thin. The pressure is way, way lower, about a third of a bar. I turn on the stove. What happens?
The water boils at about 70 degrees Celsius.
70 degrees. That's a lukewarm cup of tea. It's boiling, bubbling away, but it's not actually that hot.
Right. You can't cook pasta properly on Everest.
Now, let's go the other way. I get in a deep-sea submersible. I go down near a hydrothermal vent at the bottom of the ocean. The pressure is crushing. 50 bar, 100 bar, whatever. I turn on my magical underwater stove.
The water will get to 100 degrees, and nothing happens. It just gets hotter. It gets to 150 degrees, still nothing. It stays liquid. You can have superheated water at 200 degrees Celsius that refuses to turn into steam.
Okay, so here's the question that just blew my mind when I read this. In all three scenarios, the water molecule, the H2O, didn't change. It's the same hydrogen and oxygen. The fire, the heat source, didn't change. But the behavior of the system completely radically changed. Why?
Because of the constraint.
The constraint.
The atmospheric pressure is acting as a boundary condition. It's an external force sitting on top of the water's surface, and it's essentially saying, no, you molecules are not allowed to escape and expand into steam until you have accumulated this much energy.
It's a lid on the pot.
It's a lid on the pot. On Everest, the lid is very light. It takes very little energy for the water molecules to blow it off. At the bottom of the ocean, the lid is immensely heavy. You need a massive amount of energy to overcome that external constraint.
So the boiling point, that energy threshold for the phase transition, it's not an intrinsic property of the water itself, it's a property of the water in its environment.
Exactly. The environment sets the threshold.
And the source material argues that the quantum vacuum works exactly the same way.
This is the grand unification of the idea, the author argues. Look at the atmosphere. That is matter under a pressure constraint. Now look at gravity. That is space-time under a metric constraint from a large mass. Now look at the vacuum. That is the electromagnetic field under a geometric constraint.
Constraint writes the choir.
And the choir writes the energy ledger. If you change the vacuum constraint, just like changing the air pressure, you change the energy thresholds for any matter that exists inside that constraint.
That is such a powerful image. We usually think of, say, an atom as this independent little thing that weighs what it weighs, no matter where it is. But this suggests an atom is more like that pot of water. Its properties, its effective energy, might depend on how heavy the lid of the vacuum is pressing down on it.
Yes. Mass, inertia, reaction rates, these might all be environmental variables, not just intrinsic, unchanging ones.
Okay, I'm really feeling the aha moment. This makes a lot of intuitive sense, but I can also hear the listeners. I can hear the PhDs in physics grinding their teeth.
Oh, yeah.
Because physics is a brutal, brutal arena. You can't just say, hey, it's like boiling water and expect to win a Nobel Prize. We have to subject this to the Hostin referee test mentioned in the notes.
I love the hostile referee. Let's bring them in.
Okay, I'm putting on my cranky physicist hat. I've read the paper, I've listened to the argument, and I have objections. I want to poke holes in this. Objection number 1. We touched on this briefly, but let's drill down hard. Particle accelerators. We have spent billions and billions of dollars building things like the Large Hadron Collider. We smash protons together at 99.99999% of the speed of light. We use EMC22 to calculate everything, and the math works perfectly. If this structured vacuum thing was real, wouldn't we have noticed that our calculations were off by now?
This is probably the most common and most important objection. If it ain't broke, why are you trying to fix it? But the answer lies in thinking about the physical construction of a particle accelerator. Where do the particles actually travel?
In a tube, a beam pipe.
Right. A beam pipe that is a few centimeters wide. And what is inside that pipe with the particles?
A vacuum. A really, really good vacuum.
An ultra-high vacuum. And crucially, the beam of particles is steered by magnets right down the dead center, as far away from the physical walls of the pipe as humanly possible.
Sure. You don't want your billion-dollar particle beam hitting the walls.
So, geometrically speaking, what have we built?
We've built a tiny circular version of deep space.
We have built the best possible approximation of free space we can make on Earth. We have intentionally designed the entire machine to minimize wall interactions. We designed it specifically to have a chimidollar.
Oh. So we built a machine to look for the free space answer, and surprise, surprise, we got the free space answer.
Exactly. The beam pipe is the infinite salt flat. It's not the broom closet. The relevant wavelengths of the vacuum that would interact with something as tiny as a proton are incredibly small. To a proton, a 5-centimeter wide pipe looks like the Grand Canyon. It might as well be infinite.
So the effect is essentially invisible in an accelerator because the box is just too big relative to the particle.
Correct. The geometric cutoff frequency imposed by the walls is too low to matter for those high-energy interactions. To see this effect, you need to squeeze the space down. You need nanocavities. You need gaps that are comparable to the quantum wavelengths you actually care about.
Okay, that's a very solid defense. You didn't see it because you weren't looking in the right place with the right ruler.
Yes.
All right. Hostile referee objection number 2. And this one is a bit more philosophical. The fifth force accusation. Physics has 4 fundamental forces. We know them: gravity, electromagnetism, the strong and weak nuclear forces. If you are telling me that the mass energy of an object changes when I put it inside a cavity, that implies some new force is acting on it. Are you inventing a fifth force? Because if you are, you need extraordinary evidence.
This is where scope discipline, as the source calls it, is absolutely vital. And the answer is an emphatic no. We are not proposing a new fundamental force of nature that permeates the entire universe.
But something is pushing the Casimir plates together. That's a force.
That is the electromagnetic force. It's just the quantum manifestation of it. It's the zero-point field, which is part of the standard model of electromagnetism. We aren't adding a new ingredient to the soup. We're just pointing out that the existing ingredients behave differently when you change the shape of the pot.
It's not a fifth force. It's more like a contextual application of the second force, electromagnetism.
Right. It's what physicists would call a modification of the potential. It's like saying wind creates a force. Well, yes, but that only happens if there is air and only if there is a pressure difference. We aren't inventing a new fundamental wind force that exists in empty space. We are just describing the dynamics of the existing fluid. This theory describes vacuum dynamics.
Okay, I'll buy that. It's a structural effect, not a new particle or field.
Correct. It's an emergent property of the system.
Objection number 3. Conservation of energy. This is the holy grail, the first commandment of physics. Thou shalt not create or destroy energy. If I put a battery in a box and its effective energy value goes up, did I just create energy from nothing? Because that sounds an awful lot like a perpetual motion machine, and those are illegal in this universe.
This is the trickiest one, but it's also the most elegant answer, I think. The answer lies in the assembly of the system.
The assembly.
Think about the Casimir plates again. When they're far apart, they have a certain potential energy. When you let them go, they snap together. In that process, they release energy. They do work.
Right.
But what if you want to pull them apart again?
You have to pull on them. You have to do work.
You have to put energy in. You have to fight against the vacuum pressure to reset the trap.
Ah. Okay, so there is no free lunch.
There is never, ever a free lunch in thermodynamics. If constructing the cavity building the box changes the energy state of the vacuum and the object inside, you had to pay for that change with energy during the construction process. The energy balance sheet of the entire system, the walls, the vacuum, the object inside, and the person who built it, is always conserved.
So we aren't creating energy. We are just moving it around the ledger. We're reallocating it. We are saying, okay, the vacuum field paid for this part of the energy budget, so the mass has to pay for that part.
Exactly. It's just accounting. But it's accounting where the exchange rate between different forms of energy depends on the topology.
I really like that. Topology determines the exchange rate.
It's the perfect summary of the core claim.
Okay, we've defended the theory, we've fought off the hostile referee, but a theory is completely useless if it doesn't predict anything new. If I can't go to the lab and test it, it's just philosophy. What are the treasure maps? Where does this research say we should dig to prove it's real?
The paper is great on this. It offers 3 very specific, testable predictions. These are the experiments that could either validate the theory or kill it dead.
Okay, prediction number 1, the toroidal cavity.
The donut.
Why a donut? Is the universe secretly hungry?
No. It's about something called periodic boundary conditions. Think about a simple guitar string. It's tied down at both ends. It can only vibrate in very specific ways, certain standing waves that fit perfectly.
Right, harmonics.
Exactly. Now think of a ring, a circle. A wave can travel around that ring and bite its own tail. If the wavelength fits perfectly into the circumference, it reinforces itself. It resonates.
It's a self-sustaining loop.
Right. And the topology of a donut, which is technically called a torus, allows for a whole different set of modes for the vacuum choir than a simple box or 2 flat plates. The math is different. And the specific prediction is that if you build a donut-shaped vacuum chamber and measure the Casimir pressure inside it, that pressure will be significantly higher than standard theory predicts for a similar-sized box.
So we build a high-tech metal donut, we measure the vacuum pressure inside, and if the number is too high, then we have evidence for this chi factor.
Exactly. A deviation from the standard Casimir calculation that matches the prediction from the spectral geometry calculation would be the smoking gun.
Okay, I like that. It's concrete. Prediction number 2, corrugated surfaces.
Think of Ruffles potato chips. wavy plates instead of flat ones.
Okay.
Now, if you bring two wavy plates together, the geometry is incredibly complex. The distance between them is constantly changing at every point. Standard physics tries to handle this by averaging it out. It uses something called the proximity force approximation.
Which basically says,
It basically says, just treat it like a bunch of tiny little flat plates all added together. It's an approximation. But the structured vacuum theory says, no, the wave nature of the vacuum matters. The specific shape of the corrugation, the waviness, will create unique patterns of constructive and destructive interference in the vacuum spectrum.
yes, you should see spikes and dips in the force that the standard smoothed-out physics just misses.
Yes. You should see texture in the force field that corresponds to the texture of the plates.
That's very cool. It's like feeling the grain of the vacuum itself.
And prediction number 3 is the most high-tech of all. High-Q resonators and the Purcell effect.
Okay, high Q, that means high quality.
It means high-quality factor. It's basically a measure of how well a cavity can hold a tone or a wave. A church bell that rings for a full minute is high Q. A bell that just goes thud is low Q.
Got it.
So we can build optical cavities, tiny boxes made of perfect mirrors that can trap a photon of light and have it bounce back and forth for a very long time. If you put an excited atom inside one of these boxes, its rate of emitting a photon changes. This is a known phenomenon called the Purcell effect.
The atom glows faster or slower depending on the box it's in.
Yes. But typically we explain this with standard quantum optics, which is all about the available modes for the photon to escape into. This theory predicts a specific additional shift in that rate, a deviation from the standard Purcell calculation that would correlate directly to the Chait factor. It links the mass energy of the electron transition itself to the geometry of the cavity.
So if we can measure the glow of these atoms inside these mirror boxes with extreme precision, we might see the signature of the structured vacuum.
Precisely. And the beauty of all three of these predictions is we have the technology to do these experiments now. This isn't science fiction for the year 3000. We have the nanofabrication, we have the lasers, we have the sensitive force measurement tools. We just need to run the tests with this specific hypothesis in mind.
And that leads to the ultimate test of any real scientific theory: falsifiability. How do we kill this theory if it's wrong?
It's actually very simple. The theory makes hard numerical predictions. The first way it could die is if it turns out geometry doesn't change the spectrum.
But we know it does. Casimir proves it does.
Right. So the first hurdle is already cleared, which is why the theory is compelling. The second and final hurdle is, does that proven spectral change actually scale the energy of matter? If we build that donut cavity and the pressure inside is exactly what the standard boring textbooks say it should be, then Kadishte is a fiction. The link isn't there. The theory dies.
I really respect that. It puts its neck on the block. It says, here is the number I predict. Go measure it. If I'm wrong, I'm wrong.
That is the only way science ever moves forward. You have to be willing to be wrong.
We're coming to the end of our hour here, and I want to zoom out. We've been deep in the weeds of math and metal plates and donuts. But there is a bigger picture here, isn't there? A real philosophical shift.
I think so. It's the shift from thinking of space as passive to seeing it as active.
Say more about that.
For centuries, really since Newton, we have treated space as a container, a passive, inert box. You put the experiment in the box, and the box does nothing. It just holds the stuff.
The box is neutral. The stage is empty.
This theory argues that the box is never neutral. The box is an active participant in the experiment. The geometry is causal.
Geometry is causal. I like that.
The shape of the space determines what is physically possible inside that space. It decides which notes the vacuum choir is allowed to sing. It decides the energy threshold for boiling water. It decides the Casimir force. And if this theory holds up, it helps decide the effective mass energy of matter itself.
It reminds me of that old line about architecture. We shape our buildings, and afterwards, our buildings shape us.
That is surprisingly literal in this context. If you build a nanostructure in a computer chip, that structure shapes the vacuum. And that shaped vacuum, in turn, shapes the physics of the electrons flowing through the chip.
It changes how we think about engineering. We aren't just building machines out of matter. We are sculpting the vacuum itself.
We become vacuum engineers. That is the potential future this research points toward. A future where we might manipulate the properties of matter, not by changing the matter itself, but by carefully changing the empty space around it.
And that is a hell of a thought to leave you with.
It certainly is. The implications are enormous.
So next time you look at an empty room or an empty coffee cup, or even just the space between your fingers, remember, it's not empty. It's a choir. And it's just waiting for a conductor.
And the conductor is the boundary, the shape.
Thanks for diving deep with us. This has been a trip into the structured vacuum. Keep asking questions, keep looking at the shape of things, and we'll catch you on the next one.
See you then.
You know the one. E equals mc squared. It's probably the most famous equation on the planet, the very symbol of genius. But what if it's not the whole story? What if it's actually just a special case of something much, much deeper, where the actual shape of space itself can change the answer? Let's get into it. So, to get our heads around this idea that the shape of space could actually matter, we don't need to jump straight into mind-bending relativity. Nope. Instead, let's start with something way more down to earth, a simple cup of tea. And this really gets at the core question, right? Are physical properties, like energy, always constant no matter what? Or can the environment they're in, the context, actually change the rules of the game? Okay, so think about boiling water. At sea level, we all know it boils at 100 degrees Celsius. But if you take that exact same water up to the top of Mount Everest, it boils at only 70 degrees. It's the same H2O, right? Nothing about the water itself has changed, but its environment has. The lower air pressure literally changes one of its fundamental properties. This is a really big idea to keep in your back pocket for this whole explainer context. Context isn't just background noise. It can be causal. Okay, so if context, like air pressure, can change something as basic as the boiling point of water, well, what if it could also mess with the relationship between energy and mass? This very question is what led to a really provocative, kind of intuitive first draft of a new idea. So this was the first stab at it. Now, it's what physicists call an ansatz, which is basically a fancy word for an educated guess. Instead of just the familiar c squared, the idea here is that a particle's energy depends on how energy is moving inside it. Picture the energy that makes up a particle, right? It's not just flying off in a straight line. It's kind of bouncing around, trapped inside a tiny volume. So its average speed, what they're calling VT here, is going to be slower than the absolute speed of light, c. And this formula tries to capture that. The logic is actually pretty elegant, pretty simple. E equals mc squared, that's perfect for energy just zipping along in a straight line, free as a bird. But the energy that makes a particle, well, that's a different beast. It's trapped, it's circulating, it's in what they call a recursive closure. I mean, on the surface, it's a really neat idea, a solid first draft. But you know how it is in science. A cool, intuitive idea? That's just the starting gun. For it to become a real theory, it has to go on trial. It has to survive a pretty brutal stress test. Basically, you throw everything you've got at it and see if it breaks. And here comes the first punch, and it's a big one. It's a question aimed right at the heart of relativity. See, one of Einstein's biggest rules is that some things have to be constant for everyone. A particle's rest energy is one of them. It shouldn't matter if you're standing still or flying by in a spaceship, the answer has to be the same. So, does this new formula pass that test? The answer? A big, fat nope. That little VT term, the internal speed, well, that would look totally different to an observer who's moving. And that means the particle's rest energy, its most fundamental property, would literally depend on who's measuring it. That's a huge problem. It completely violates a core tenet of relativity called Lorentz invariance. This was a fatal flaw, a real deal breaker. Okay, so flaw number one. That's a major blow. But wait, there is more. Let's look at another scenario, a super common one in physics, a standing wave. Where energy is basically trapped, just sloshing back and forth, but the overall flow is zero. And this is where the whole idea just completely implodes. In that standing wave, since the energy isn't really going anywhere, its average transport speed, that VT, is zero. And what happens when you divide by zero? Yep, you get infinity. The formula predicts infinite energy for a simple standing wave, which is, impossible. So that's the second fatal flaw, the nail in the coffin. The elegant first draft, totally fundamentally broken. Okay, so you'd think that's the end of the story, right? Idea's dead. But this is where it gets really interesting. Because the core concept, the idea that geometry itself can affect energy, it doesn't just go away. It just needs a much, much stronger foundation. And it finds that foundation in a real, measurable, and honestly, kind of bizarre effect from the real world of physics. Enter the Casimir effect. Now, this isn't some pie-in-the-sky idea. This is a real, experimentally verified phenomenon. Here's the gist. You take two perfectly neutral metal plates, put them super, super close together in a total vacuum, and a force pulls them together. Out of nowhere. And why? Because it turns out that empty space isn't empty at all. It's fizzing with this sea of background quantum energy, the zero-point energy. And those plates, just by existing, their geometry, their presence, actually changes the nature of that energy. Right, so you can picture the vacuum as this ocean of energy waves, every possible size and wavelength all jumbled together. But when you stick those two plates in there, you create a boundary. Now, only waves of a certain size can fit perfectly between the plates. You've restricted the spectrum. You've filtered out some of the waves. So now you have more energy on the outside pushing in than you have on the inside pushing out. And that difference in pressure, that's the Casimir force. It's real. It's proven. Geometry is directly changing the energy of space. So now, with the solid, proven physics of the Casimir effect as our anchor, we can rebuild the original idea. This is what we'll call the hardened thesis. We're throwing out the guesswork and building this on the real physics of what's called spectral geometry. And this gives us a new, much more robust term, chi sub t, the topology factor. See, we're not guessing about some internal transport speed anymore. This is something you can actually calculate. It's a precise ratio. You take the energy density in your bounded, confined space, and you divide it by the energy density you'd find in totally free, empty space. What you get is a number, a factor, that tells you exactly how much that specific geometry has altered the local energy of the vacuum. And what's so great about this new approach? It just elegantly solves both of those fatal flaws we talked about earlier. Remember the frame dependence problem? Gone. The topology factor is defined in the rest frame of the object, so it's the same for everybody. Problem solved. And the standing wave paradox, the whole dividing by zero thing, well, this is based on spectral density, not flow. So even if the energy isn't going anywhere, it's still there. The density isn't zero, so the calculation works. You get a real finite answer. Both problems, just gone. So what we have now is this chi factor, and it's a thing of beauty. It's robust, it's precise, it's a pure number, no units. And it depends on two things, the geometry of the space and the material its boundaries are made of. And here's the kicker. In that perfect, idealized empty space you read about in textbooks, its value is exactly 1. And maybe most importantly, this isn't just some number you pull out of thin air. You compute it straight from the underlying physics. So where does this leave us with good old E equals mc squared? Well, it means we have to look at it in a whole new light. The equation isn't wrong, not at all. It's just a special case. It's incomplete. It describes a very specific, very idealized situation. Here's the big picture this theory paints. In the general case, in any real bounded space, the equation would actually be E equals mc squared times our new topology factor, chi t. And Einstein's famous formula, that's just the special case. That's what you get when you're in perfectly empty, unbounded space, where chi t just happens to equal 1. So E equals mc squared times 1 is just E equals mc squared. It's not the whole story, it's the ideal story. There's a quote from the source material for all this that I think just nails it. It says, "Topology is not decorative, it is causal at the spectral level." What that means is the shape of things, their geometry. It's not just for show, it's not decoration. Down at the most fundamental level, the level of the vacuum's energy, that shape is actually a cause. It actively dictates the energy that a system can have. And that just leaves us with this incredible, mind-bending question to chew on. You know, we usually think about the universe as being made of stuff, right? Substance, particles. But if something as fundamental as energy can be shaped by its geometric context, what else out there is determined not by what it's made of, but just by its structure, its shape?